Okay, so today we're going to be talking about integration by parts. Integration by parts is a very good tool for solving integrals, more powerful than substitution rule and regular antiderivatives. It allows us to solve things such as the integral of x sine x. In integration by parts, we have such a thing called LIPET, which stands for logarithms, inverse trigonometric, polynomial, exponential, and trigonometric functions. LIPET tells us when we should be using integration by parts, when these functions are present. LIPET also gives us an order in which we should prioritize these functions, from logarithms to inverse trig to polynomials and so on. Now, in integration by parts we use a formula, which is the integral of u dv equals uv minus the integral of v du, or the integral of uv prime equals uv minus the integral of vu prime.
We're going to start by deriving the integration by parts formula. And for this, we'll need the product rule formula, which states that the derivative of the product of two functions, u and v, is equal to the derivative of the first function times the second function plus the first function times the derivative of the second function. And to get the integration by parts formula from this, we simply integrate this whole equation. So when we integrate this side, we're integrating the derivative of uv, so we'll just be left with uv is equal to the integral of u prime v plus the integral of uv prime. And now we can easily rearrange this to get the integration by parts formula. The integral of u prime v is equal to uv minus the integral of uv prime.
Alright, so our first example is the following. We have the integral of x squared e to the x dx. So in this case, u would be x squared and dv would be e to the x dx. The derivative of x squared du would be 2x dx, and the antiderivative of e to the x dx is simply e to the x. So we can rewrite the integral as x squared times e to the x minus the integral of v du, so 2x dx times e to the x. Now we can bring the 2 outside the integral, so we're left with x squared e to the x minus 2 integral of x e to the x dx. Now you'll notice that we can once again simplify this integral right here. So u would be x and dv would be e to the x dx. The integral of x is simply dx, and the antiderivative of e to the x dx is once again e to the x. And now we're left with x squared e to the x minus 2 uv, so x e to the x, minus the integral of v du, so e to the x dx. And now we simply expand, so we have x squared e to the x minus 2x e to the x plus 2, and the integral of e to the x dx is simply e to the x. And we can factor out the e to the x's, so we have e to the x times x squared minus 2x plus 2 and let's not forget the c. And this is our answer. A faster and more efficient way of integrating by parts is by using the tabular method. Nonetheless, the process is similar to the integration by parts formula method. First, we begin by drawing a table with two columns. One for the component to be derived, and the other for the component to be integrated. In this example, we'll be deriving f of x and integrating g of x. So f of x would become f prime of x, and g of x would become the integral of g of x. Every other derivative is multiplied by -1. We repeat this process until the component being derived becomes 0, or until both components are repeating. Now, for the purpose of this exercise, we'll pretend that the third derivative of f of x is 0. Afterwards, it is a question of adding the product of the diagonal terms going down and to the right. So here we would have f of x times the integral of g of x minus f prime of x times the integral of g of x plus f prime prime of x times the integral of the integral of g of x. If both components were repeating, the last term in the expansion would be the integral of the product of the last row of the two terms on the last row. And this is the generalized tabular method.
In the next example, we're going to integrate 2x cubed sine of 2x using the tabular method. So to start this, we'll draw the table with our deriving side and our integrating side. And we need to choose a component of our term to go on the deriving side and the rest to go on the integrating side. And since x cubed is a polynomial, it can be repetitively derived and eventually reach 0. So we're going to put x cubed on this side and the rest 2 sine of 2x on this side. And we'll put a plus since the deriving side alternates signs. So on the second line, it will flip to a negative sign. And we'll derive x cubed to get 3x squared and integrate 2 sine of 2x using chain rule to get negative cosine of 2x. And we flip the sign and derive again 6x and integrate for negative half sine of 2x. Now since negative half sine of 2x is a multiple of 2 sine of 2x, we know that this side is repeating now. And we only have to wait for the deriving side to either start repeating or reach 0. So on the next line, we'll flip to negative, derive to get 6, and integrate for 1/4 cosine of 2x. And again, plus now 0, 1/8 of sine of 2x. So now we've reached 0 here, and this side is repeating. So both sides have stopped, and we can find the final answer. So to do this, we multiply and then add diagonal elements. So first we'll multiply this element and this element, x cubed and negative cosine of 2x. Multiply these together and we'll get negative x cubed cosine of 2x. And we'll add that to the product of the next two diagonal elements, 3x squared and negative half sine of 2x. And when we multiply these together, we get plus 3 over 2 x squared sine of 2x. And then these two terms, plus 3 over 2 cosine of 2x. And finally these two terms, minus 3 over 4 sine of 2x. And since this side has run out of elements, we're finished. This is our final answer. And that's how you integrate 2x cubed sine of 2x.
So today I will be solving the following integral. Integral of sine 3x times cosine 7x dx. I will begin by assigning the following values. U equals sine 3x and dv equals cosine 7x dx. Therefore, du equals 3 cosine 3x dx and v equals sine of 7x over 7. We get the following. Integral of sine 3x cosine 7x dx equals sine 3x times sine 7x over 7 minus the integral of sine 7x over 7 times 3 cosine 3x dx. We will now call this I2. When we rearrange, we could find that I2 equals 3 over 7 times the integral of sine 7x cosine 3x dx. To solve this, we will now assign u equals cosine 3x and dv equals sine 7x dx. Therefore, du equals negative 3 sine 3x dx and v equals cosine 7x over negative 7. We get I2 equals cosine 3x times cosine 7x over negative 7 minus the integral of cosine 7x over negative 7 times negative 3 sine 3x dx, and everything multiplied by 3 over 7. After rearranging and simplifying, we could now determine that our original integral I now equals 1 over 7 sine 3x sine 7x plus 3 over 49 cosine 3x cosine 7x plus 9 over 49 integral sine 3x cosine 7x dx. But wait, That is our original integral I. Comes the best part, because we could substitute the original I back into the equation. We get that I equals 1 over 7 sine 3x sine 7x plus 3 over 49 cosine 3x cosine 7x plus 9 over 49i. We could then put I onto the other side of the equation, isolate it, and get that I equals 1 over 40 brackets 7 sine 3x sine 7x plus 3 cosine 3x cosine 7x. And finally, after some rearranging, we could get that the integral of sine 3x cosine 7x dx, which is our original integral I over here, equals 1 over 40 times 5 cosine 4x minus 2 cosine 10x.